Long-range flights across remote areas, and especially over oceans and polar regions, which are areas without airfields, radio stations, ground-based navigation aids, or any other facilities, bring their own particular set of problems and considerations. This lesson will examine the equipment, techniques, and procedures which have been developed over the years to make such navigation as safe and efficient as possible. Polar navigation routes take advantage of the shorter distances afforded by Great Circle tracks. Since the majority of the world's landmass is in the Northern Hemisphere, most of the commercial flights that use polar routes are over the Arctic. At the high latitudes involved, and polar navigation can be considered to be on north-south tracks north of 65 degrees north, and particularly over the northwest Atlantic and northeast Canada and Greenland, magnetic compasses become more difficult to use reliably because of the large and relatively rapid changes in magnetic variation in flight. The magnetic North Pole being located in northeast Canada to the west of Ellesmere Island. It is not in a fixed position, hence the ubiquitous constant small changes in variation, and in 2009 was moving northeastwards at about 60 kilometers per year, or about 6.8 meters per hour. It also has an elliptical diurnal oscillation up to 80 kilometers from its mean position. If an aircraft were to be positioned between the magnetic and geographic North Poles, the variation would be 180 degrees. That is to say, magnetic north would be true south. The potential for error if relying on magnetic compasses to navigate can be easily seen from the diagram. To avoid the problems of the magnetic compass, navigation is achieved using INS or GPS, or the technique of grid navigation, in which gyro compasses are run in gyro mode and aligned to grid north for the chart being used. Grid navigation and the use of polar stereographic charts are fully covered in the Navigation General Syllabus. True north can of course be used as a reference for navigation, and in the Canadian Northern Control Area, VORs are orientated to true north, instead of the normal magnetic north to aid pilots flying on grid. Shown as an example is Resolute Bay, Canada's most northerly town, which is on an island between Ellesmere Island and mainland Canada, about 600 nautical miles south of the magnetic North Pole, and with a variation of more than 31 degrees west. Because of the variety of navigational methods usable in the polar regions, it is very important that the systems are carefully monitored. Particular care is required when the autopilot is slave to one of the navigation systems, and position comparisons should be made frequently against an independent source of position information. For example, a comparison of an inertial navigation system with GPS, or GPS with a VOR DME position line. Care is also required if the autopilot is disengaged for any reason, for example turbulence, that the desired track is recaptured and maintained correctly when it is re-engaged. The gyro compasses may also need frequent realignment, depending on the type of gyro fitted, because of the prevalent high rates of earth rate and transport wonder in this area of the world. Other factors which contribute to the difficulties of polar navigation include radio communications, which are often limited to HF because of the long distances between stations, and the scarcity of ground-based navigation aids and en route alternate airfields, due to the remoteness, inhospitable terrain, and harsh climate. Transoceanic flight presents similar problems to flying over large areas of remote and sparsely populated land. That is, communication difficulties, because of a necessary reliance on HF radios, being out of VHF range, no radar, and no permanent radio navigation beacons. In addition, of course, oceans tend to be much larger than most remote land areas, and present very little opportunity of finding a place to land on solid ground in the event of an emergency, other than mid-ocean island groups such as the Azores and Ascension in the Atlantic, and the Hawaiian Islands and Polynesia in the Pacific. Such an event did actually occur in August 2001, when an Airbus 330 of Canadian carrier Air Transat, flying from Toronto to Lisbon, suffered a double flameout, that is, the loss of both engines, due to a fuel leak in the right engine, which was exacerbated by an attempt to rebalance the fuel by cross-feeding. This unfortunately pumped more fuel overboard, and resulted in the aircraft running out of fuel. But the captain, who had already initiated a low-fuel diversion to Lajes Air Force Base in the Azores, managed to glide the Airbus to a landing at Lajes, saving all 306 people on board, with only 18 minor injuries. The aircraft was only slightly damaged and was returned to service. As a footnote to this story, it is worth noting that the flight crew were criticised for not correctly diagnosing the original fault, the engine fuel leak, but praised for a remarkable piece of flying. The fuel leak was caused by an incorrect hydraulic part chafing through the adjacent fuel line, for which Air Transat took responsibility. Had the flight not been rerouted further south for traffic reasons, the aircraft would not have been able to glide to Lajes, and that is one link in the chain of events which prevented a tragedy. When flying in oceanic airspace, aircraft cannot be monitored by radar except close to land, and therefore air traffic control has to be procedural. This means that it is based on the flight being given a cleared route for the ocean crossing, with an entry time which is based on the estimate passed by the pilot when he requests his oceanic clearance, but which may be adjusted by the Oceanic Area Control Centre, or OAC, depending on traffic. As part of procedural control, the pilot has to make position reports on HF radio to the appropriate OAC, or OACs if crossing a boundary, at each waypoint on his cleared route, typically every 10 degrees of longitude when flying east or west, or every 20 degrees of latitude above 70 degrees, giving actual time of arrival at the point, flight level, next waypoint and estimated time of arrival, and the next point on the route. Also included would be other information such as climb requests and mandatory reports of significant or severe weather, usually icing or turbulence. Because of the lack of weather observation stations, aircraft flying on random routes will add weather reports, consisting of ambient spot wind and outside air temperature, to the position report. Random routes means effectively most routes outside the organised track system, of which more will be covered in the following lessons. If a flight crew are unable to comply with their clearance for any reason, a revised clearance should be obtained where possible before any action is taken. There are, however, procedures laid down to ensure vertical and lateral separation in the event of such things as emergency descents, if clearance cannot be obtained immediately. Oceanic routes will start at the boundary of an Oceanic Control Area, or OCA, at a point defined either by latitude and longitude or a waypoint name called an oceanic entry point, possibly at the end of an airway, as with many of those for European boundary points. By international convention, the names all have 5 letters. Those off the Newfoundland and Labrador coast of Canada are named after fish and seafood, in deference to the local fishing industry, and are even referred to in publications as the fish points. Aircraft will also leave the OCA through recognised waypoints, referred to in this case as oceanic exit points. There are no permanent fixed routes like airways within oceanic airspace, other than a few special routes, usable under specific circumstances. Instead, waypoints inside the oceanic control areas will be defined by lat and long coordinates, usually whole or half degrees of latitude, and whole degrees of longitude every 10 degrees, or 20 degrees if above 70 degrees latitude, unless the route is defined by the organised track system, which will be described in a later lesson. The distance between lines of longitude 10 degrees apart will vary with track angle and latitude, but around 50 to 55 degrees north will be in the order of 350 nautical miles. Routes are flown along the arcs of great circles between waypoints, that is, the shortest distance, and the oceanic portion of a flight's route will normally be defined by the minimum time track, or MTT. The MTT is now invariably calculated by computer to give a track which takes advantage of the wind structure along the route, using a database of both forecasts and observations to find a route which is not necessarily the shortest in distance, but which takes the least time, as its name implies. The computer will thus take advantage of tailwinds, but avoid headwinds as far as possible, either vertically or horizontally, to balance time against fuel consumption. A lower level at a slightly higher fuel burn rate may be better than going higher for better fuel rate, but into a stronger headwind. This lesson has given you an insight into the problems and considerations necessary for long-range flights in polar and oceanic regions. The busiest oceanic airspace in the world, which includes a polar region, is the North Atlantic. The special rules and procedures which apply to the area are covered in the next lesson, which in turn is followed by a short lesson on extended twin-engine operations.